So what we're going to look at today is limits, the idea of what a limit is and formalize it. We've informally looked at it in the CPM material. We're now going to formalize it as we look here. The idea of a limit is needed so that we can understand the idea of your derivative and be able to get that worked out. The notation of what a limit is, we would say limit as x approaches a of your function f is equal to a number, we'll call it L. We would read this as your limit as x approaches a is L. The informal description of a limit is if you get arbitrarily close to um, a as x approaches a on each side, the output of your function, so as you're really close to a on each side of your function, the output, the y value, should be getting really, really close to L. So there's a couple ways we can do that. But if we look at this one here, we know that we're undefined at 1. We're told that here, but we also know we can't use 1 because we divide by 0. Now, if you did go ahead and try to put in 1, you would actually get 0 over 0 here. 0 over 0 is referred to as an indeterminate form, which means you cannot determine your answer till you do more work. But we can still investigate what our limit would be. What is the output of this function right here as you try numbers really, really close to 1? So one way to look at that is to go ahead and say, well, we could look at it graphically. And looking at it graphically, we could say, let me change this. If you get really close to each side of 1 here, which would be this region right here, what is the output getting close to? So that's the y values right here. And as you get closer and closer here on each side, you can see the output, the height, gets closer and closer to 3. So you can investigate it graphically. We can also investigate it with a table. We're trying to look at our limit as we approach 1. So we look at our table and we try numbers that are closer and closer to 1 on each side to see what the output's getting closer. And as you try numbers closer and closer to 1 on each side, you can see that the output gets closer and closer to 3 in this case, which does match our graph. So how does this actually work out symbolically? So you should realize that the top is differences of cubes, so you could factor that as differences of cubes. And then you realize you have an x minus 1 over an x minus 1, so they drop out. And then we have this. Now we can actually plug in 1 for our x and our other x, and we get 1 plus 1 plus 1 is equal to 3. So you can investigate limits graphically, numerically with a table, or algebraically, symbolically, by doing some algebra. In either case, we ended up getting the exact same value no matter how we did it. So let's go ahead and take this and investigate this limit in 3 different ways. For the most part with limits, you want to just take 0, which you're approaching here, and plug it in. Well, if we did that, we get 0 on top. We get the square root of 1 minus 1, you get 0 on the bottom. Once again, you get 0 over 0. Whenever you get 0 over 0, that's an indeterminate form, so you have to do more work. One way to work this out is to put this into your y equals, and then you'd want to graph it and look at what's the output of your function when your input is close to 0. So if you would look at your graph, you would end up getting this. Now you can see as you approach x being 0 on each side here, just how far left and right are you from the y-axis, because that's x being 0. You can see that the output, the y value, is about 2. So we would say our limit is 2. Now to investigate this numerically, I would still have this in my y equals on my calculator. But now we're going to look at your table of your calculator. But I want you to go second window, which is your table set. Then arrow down to your independent, which is normally on auto. We want to switch it to ask. So table set, which is second window, switch it to ask. Then you want to go ahead and go second graph, which is your table. Now you can start plugging in different numbers for x. You could type in -1/2, and then it would spit out this. You could type in -0.1, and you would get this. -0.01, and you would get this. And you could type in all these values of x. Notice we're getting closer and closer to 0 from the left-hand side here, from the negative side. And then on this side here, we're getting closer and closer to 0 from the right-hand side or the positive side. And you can see as you look at your outputs, you're getting closer and closer to 2 from each side. So that's looking at it numerically. Symbolically, we're dealing with a root. So you'd want to go ahead and get the root out of the bottom to see if that would make a difference. So we'll go ahead and do the conjugate, FOIL out the bottom, probably keep the top the same. You notice the bottom simplifies down to just x. You get x times the top, x times the bottom. That's a special form of 1. So now we get this. So now we could actually take and plug in 0 for our x, and we get the square root of 1 plus 1. And you know that that is 2. So investigating it from all three ways, we see visually, graphically, it's a 2. Numerically, we're at 2. And algebraically, we're at 2. So a limit does not always exist. It often will exist, but not always. So what are some ways that a limit fails to exist? If we look at this right here, graphically it's over here, but to help you understand your graph, absolute value of x over x. Well, if you try a positive number, a number to the right of the y-axis, you should remember that your absolute value would do nothing, so the top and bottom would be the same. In other words, you'd always get 1 out. However, if you tried a negative number, the top's going to be positive, the bottom's going to be negative, so you know you're going to get a negative, but they'd actually be the same value, just one positive, one negative, and so therefore you get -1. So that's why the graph looks like it does. However, we would say our limit as x approaches 0 fails to exist, because from the left side, as x gets closer and closer to 0, we're approaching a height of -1. But when x is greater than 0, when we're approaching from the right-hand side, we're approaching a height of +1. So we would say your limit fails to exist because you're not approaching the same number from both sides. So if your left-handed limit and your right-handed limit are approaching different heights or different values, then your limit does not exist. Now here's another situation where your limit would fail to exist. Basically, what's going on here is we're having a vertical asymptote. As you approach from the left, we would say we're going up towards positive infinity. As we approach 0 from the right, your function follows or goes up forever to positive infinity. So we would say your limit does not exist. Your limit will exist if you are approaching the same number from each side. Infinity is a concept. It is not a number. So you have to be approaching the same numerical value from both sides for your limit to exist. So whenever you have vertical asymptotes, when you're diverging off to infinity, that means you are not having a limit. So if you are approaching the same number from each side, like this here, we would say your limit is converging to the value of 2 in this case. Or here, your limit was converging to the value of 3 in this case. If your limit does not approach one particular number like this here, we would say it diverges towards infinity. Your limit does not exist because it's not approaching a single number. We would say it diverges. Now, another way your limit could not exist would be if your function just starts to oscillate more and more, because you know the sign of anything is always between 1 and -1. Now, if you try graphing this, you would get these values coming in, and as you get closer and closer to x being 0, your function just goes up and down faster and faster and faster and does not approach one particular number. So it does not converge to a certain number. It just starts to oscillate in between two values. So we would say, therefore, your limit would not exist. So to kind of formalize your definition, it says, suppose f of x is defined on an open interval near the point C. We would say that your limit is f of x approaches C, which we would write as this, is L, provided that for any small positive number, epsilon, meaning slightly greater than 0, there's a corresponding delta, which is greater than 0, such that the absolute value of your function minus your limit is less than epsilon. For every value of x minus c has to be between 0 and delta. Now, you could look at it that way. For me, I prefer to look at it like this. Basically, I like to say my function is between my limit plus epsilon and my limit minus epsilon. So my limit right here on the graph is just below my limit plus epsilon and just above my limit minus epsilon whenever I try something on delta units on each side of C. So C plus delta and C minus delta. So if I'm ever in this region here just to the right of C or to the left of C, my output of my function is always in between these two right here. That's what the limit is talking about. We don't necessarily really care about what's going on at the value of C, just what's going on each side of C. Is that limit getting closer and closer to a certain number? So we don't really care about what's going on at the actual value of C. And that's what this is saying right here. We just want to know what's going on in each side. We call that a neighborhood. So the idea of a limit, we would say our limit of our function as x approaches C, we can get closer and closer to that limit as we get closer and closer to that value of x that we're putting in. In other words, your function gets closer and closer to your limit, the output, as you get closer and closer to that value of C, the input. So how do we go ahead and prove limits? Now, for the most part, when you're trying to figure out a limit, you take the value of x and you plug it in. If it works and you get a nice normal number, that's great. That's pretty much your limit. If we take 3 and plug it in, we get 39 minus 29, which we know is 10. So we would say our limit is 10. But how do we go about proving that? Well, that's where we need to go ahead and use this right here. We want to use this and then solve the inside for x. So in other words, we want to take our function right here. We want to put it between what we think is our limit, which is 10, plus epsilon, and our limit of 10 minus epsilon. Now all we have to do is go ahead and solve this for x. Well, to solve this for x, I'd have to get rid of this minus 29, so I'd have to add 29 to everything. Then I'd have to divide everything by 13. So what we had back here in the previous screen says that we should have been at our value minus something, and our value for that x was approaching plus something. Well, what we have here, when we solved this, we ended up with 3 minus something and 3 plus something. In other words, we were in a neighborhood on each side of 3. And that's what we should be, because that's what x is approaching up here. So in this case, our a is 3, which is good because that's what we have up here. And what does our delta correspond to here? Our delta corresponds to the epsilon over 13. So since we ended up with a neighborhood on each side of 3, because we are 3 minus something and 3 plus something, which our x was approaching, that means our limit here was 10. That's how you prove your limit. Now, suppose we take the same problem and we said our limit was 23. We know that's not our limit, but for argument's sake, what happens if you have the wrong limit here? Well, you'd still take your function, you take what you think is your limit, and you go ahead and solve it by adding your 29 and dividing by your 13. And the issue is we end up with a neighborhood on each side of 4. 4 plus something and 4 minus something. So we're ending up on a neighborhood of each side of 4, which we know is not right because we should end up with a neighborhood on each side of 3. So that means we got issues and that this is not our limit because we did not end up with a neighborhood on each side of 3. Cool. We're done.